Hello APCAL class, we're going to take a look at section 4.6, which is going to concentrate on doing the integral of the natural log function. And well, it's actually where the outcome is going to involve natural log. So the forms, for the most part, that we're going to be looking at are going to be integrals where you have x to the first power in the denominator. And now sometimes we're going to be able to just use our u substitution, but what we're going to recognize in most of these is that we get a form where we have something in its most basic form. It'll be like 1 over x that we're going to try to integrate. Now, if you remember, the derivative of ln of x was just 1 over x, and the derivative of ln of u was, u prime over u. If you remember some of those, derivatives that we worked on, some of the special ones, derivative of ln of x, 1 over x, and then if it was, let's say if it was the derivative, let's say if we're doing the derivative of, let's make it something a little more complicated, like ln of like x squared, for example, then we would say, u prime over u being the x squared, so u prime would be 2x over x squared, and then we just simplify it from there, and we get like 2 over x for the answer there. Okay, so then when we're going to, since we know that integrals, derivatives are inverse functions of one another, if I was to take the antiderivative of 1 over x, well, now that's going to be ln of x. And then since it's an indefinite integral with no bounds, we have to say plus c at the end. The other thing that we need to do is we need to put absolute values around the x, just to ensure that it says, although it may not seem very important to place absolute value symbols around your x or u, it's important to do so just to safeguard against the potential to take a log of a negative value, which is impossible. Okay. The other thing I just want to point out, it might be tempting, like if you see a problem like this one in example 1, and you might forget about this form, and then you're like, oh no, here's all that we do is we call it 2x to the negative 1, and then we try to use our power rule, which would be a logical thing to try. But what you notice when you try to do that, if I add 1 to the negative 1, I get 0. So I get 2x to the 0, and then I would be dividing by 0, right? And now you've got something, that's undefined because we end up dividing by 0. So this is where you have to recognize this is one of those special forms that, when I were to take the derivative of a natural log, it was 1 over x, or in this case 2 over x, but we know that, if there's a different constant there, I usually just take that out. And so then I would have this expression, right? And so now I know that this is just going to be 2 ln of x. And we do need to put it in absolute values, so try to remember to do that. And because this is an indefinite integral, I would put plus c at the end of that. Okay. Now in this case, if you do have an expression such as this, you're probably going to want to just let u equal the 4x minus 1. And therefore du is going to equal 4 dx. And because I only have a 1 dx, let's divide that out. So 1/4 du equals dx. Okay, so then I'm going to pull 1/4 out here, and I'll just have 1 over u du, and therefore the antiderivative of the 1 over u is just going to be ln of u, so I've got 1/4 ln of absolute value of u plus c. And then we're going to plug back in for u. We're going to put in the 4x minus 1. Okay, so that'll be 1/4 ln absolute value of 4x minus 1. I'll tack on my plus c right there. Okay, so that's what we're looking for is, that form. And on most of these, especially, when we see that we've got something that has a degree of 1 bigger than what's in the numerator, that's usually what you're looking for in this case, because in the original form, you have x to the first on the bottom and then just the constant 1 on top. And so if we do have this situation where we've got, like even a second degree in the denominator but a first degree in the numerator, if their degree kind of differs by 1 like that, the technique of letting u equal the denominator will work almost all the time. Okay, so if I let u, in this case, if I let u equal the x squared plus 1, then du would equal 2x dx. So 1/2 du would equal x dx. So, and I should have set up my integral here first, but it says find the area of the region bounded by the x-axis and the line x equals 3. And so with this graph, what we're looking for there is, our integral is a definite integral, so it's going from 0 to 3. So with this graph, I maybe should have just pulled up the graph, but since we're bounded to the line x equals 3, that'll be our upper bound, and the x-axis would obviously be what we're finding the area under. As far as why are we starting at 0, I should probably put this on a graph here, and we should examine that a little bit. So if we were to graph this one, oops, let's clear this. Okay, so it was x over x squared plus 1. Okay, so where is my, there it is. Okay, x divided by x squared plus 1. And take a look at that graph. Okay, so maybe zoom in on this just a little bit. Okay, so we're looking from 0 to 3, and it probably should have told us, that we were bounded by the y-axis. I don't think it said that, but I think that was supposed to be in there. The x-axis line x equals 3. I think it should have said the y-axis as well, just so that we know that we're starting at 0, but that was the intention of this problem. Okay, and so when I set this integral up, I'm going to have x, so the antiderivative of the expression x over x squared plus 1, and it's bounded 0 to 3 so that we can find that area that they're asking us about. Okay, and so now I have already set up my u substitution right over here, right? And so when I substitute these values in, I should have a 1/2 on the outside. So I'll have 1/2, the antiderivative 1 over u, derivative of 1 over u and du, right? And now remember, there's more than one way you can do this. If I leave it in terms of u, then we would have to change, these are x values, the 0 and the 3, right? So 0 now, if x is 0 in here, then u would be 1 when it's in terms of u, because I plug it in here, right? 0 squared plus 1. And if x is 3, 3 squared plus 1, that would be 10, right? And now when I do my antiderivative of this, it's going to equal, it'll be 1/2 ln of absolute value of u and that's going to be evaluated from 1 to 10 if I leave it in terms of u. Okay, and so if I want to evaluate this, then I would just have 1/2 ln of 10 minus 1/2 ln of 1. And that would be 1/2. Now, the ln of 1, if you remember that one, because remember, this is base e, so if you think about this, e to the 0 power equals 1. Anything to the 0 power equals 1. And so an ln, or any log of 1, is always 0, so this ends up just being 1. Sorry, not minus. 1/2 ln of 10 minus 0. And so it's just going to be this for my solution for that one. Okay. All right, example 3. So here we have, it says with proper insight, these integrals should be easy to solve. And so again, if we see the trig ones are just a little different, but for the most part, I think if you're recognizing, if you take the derivative of the denominator, you get close to or exactly the numerator in these ones, and so they're pretty easy u substitutions. So if u equals x cubed plus x, then du is going to equal 3x squared plus 1 exactly, right? So that's easy. That's just 1 over u du, which is ln of absolute value of u, plus c, and if we substitute back, that's ln of the x cubed plus x, and then plus c at the end of that. Okay. All right, for part B, we've got, if we let u equal the denominator again, tangent of x, then the du is going to equal secant squared. And so therefore, again, it's just going to, that'll fit perfectly as 1 over u du, right? And so when we integrate this one, we're just going to have ln of u, and therefore it's just ln of u is tangent of x, so ln of absolute value of tangent of x plus c. Okay, I didn't have a lot of space in these, I apologize for that. If we let u equal x squared plus 2x on this one, du would equal 2x squared plus 2, or sorry, not 2, just 2x plus 2. And in this one, you can see this is only x plus 1, this is 2x plus 2, which if I factor out a 2, I'll get that. And so it would be like 1/2 du equals 2x plus 1. Oh, not 2 anymore, I divided that out. Just x plus 1. So I'll have 1/2, and then pull that out, and then it'll just be 1 over u du again. And so that would be 1/2 ln of u plus c. So that would be 1/2 ln absolute value of, and u was x squared plus 2x. Okay. And I think part D, maybe I'll just skip over that. It's going to be similar. Let u equal to 3x plus 2, and then you'll end up having to, it'll be you'll have a 3 that you'll have to divide out, so there'll be a 1/3 in front of your integral. So you could maybe even just think ahead to the answer. It's going to be, you'll have to divide by that 3, so it's going to be 1/3, and then you'll have ln of 3x plus 2 plus c for this one. They all kind of follow that pattern. It's pretty easy. Okay. Okay, now these ones say when normal u substitution is not a viable option, which means that you're going to have to do like a change of variable method on some of these, and then there's one other method here that's a little bit different. I'll talk about this one. It's a long division problem. Okay, so in this one, if we let u equal just the x plus 1 again, then du is going to equal just dx. But again, if that's the case, we have a 2 here, right? So we could probably just pull that 2 out, but we need an x, right? So if we go back here and do that change variable method, solving this for x, I'd have x minus 1, I'm sorry, u minus 1 is what x would equal. So x equals u minus 1, right? And so in this, I'd probably pull that 2 out right away. And then for the x, I substitute u minus 1 on top. And then on the bottom, I will have u squared. And then I've got my du there, right? Du for the dx. Okay, so now this one, because I have like those 2 pieces in the numerator, I can set these each over, a separate denominator and just have individual terms in this case. And so, u over u squared, that would simplify down to 1 over u, and then 1 over u squared would just be 1 over u squared. And so, if I'm going to integrate this, this first piece is going to be ln of u, right? And that's why this is different from what we've seen before. 2, and then I'll have ln of u for this piece. But this one I just use a power rule because this is the same as u to the negative 2. So if I, do the antiderivative of that, that's going to end up being u to the negative 1 divided by negative 1, which is going to change this to just plus u to the negative 1, right? Or 1 over u if you want. Okay. So this, actually I put that in absolute values as well, and then when I go back and substitute ln of absolute value, and since u was originally x plus 1, I would have that, and then plus the u to the negative 1 would be 1 over u, but then again that would be 1 over x plus 1, like that. And then let's tack on a plus c, since it is an indefinite integral. Okay. And the last one I'm going to do in this set of notes, we'll do the trig ones in the next video. So if you see this is the case, and you have the same degree, and these are polynomials that are, not, you have something that's a polynomial in the bottom that's not like a monomial, it has like two terms. Usually what you want to do with something like this, when these degrees are the same, is use long division. It's maybe been a little while since you've done long division, but here's how this looks. Polynomial long division. You did a lot of synthetic division, I think, in Algebra 2, and if you took college algebra, we did that. But that only works when you're dividing by a linear polynomial, and since that's quadratic, we're going to have to use long division for this. Okay, so I filled in a 0x in the middle there, just so that we have all the placeholders. And x squared goes into x squared, obviously, just once. So I'm going to put a 1 up here as part of my quotient. When I distribute that through, x squared plus 0x plus 1. Now I'm going to subtract. This is 1x minus 0x, so that's x. And, or that's all I'd have there. And then here, I got nothing, right? So my remainder basically is just x. So what you do, remember you put the remainder over the divisor, so it would be plus x over x squared plus 1. I'll just go back to that. That's my divisor. Now that it's in this form, this is just an equivalent form of what I have here. It's almost like if this was an improper fraction, this is the mixed number form of it, but it's with polynomials. But when it's in this form, it's going to be a little easier for us to integrate, especially this second piece, which represents the remainder over the divisor. Okay, so when I have this now, obviously the antiderivative of 1 that's easy. That's just going to be x, so that's easy enough. So maybe I'll just do x plus, and now I'm going to integrate this part. And this is the one where I'll have to do a quick maybe u substitution would be okay. But on this piece, that you can see if you let if u equals x squared plus 1, and du then equals 2x dx, which means 1/2 du equals x dx. Right? So now we've got that. That'll all substitute. I'll just have a 1/2 up front. So in my answer, I'll change back to blue here. So I will still have that x plus, so I'm just recopying what I had here. Now this antiderivative part here, I'll have the antiderivative of, and I'm going to put a 1/2 out here, 1/2 the integral, and then this is 1 over u du, which means 1/2 ln of u plus c, and then I'm going to put that my u value back in there, which was x squared plus 1, so I had x plus 1/2 ln x. And in this case, I don't really need the absolute value, because if it's x squared plus 1, that cannot be negative. You're squaring x, and then you're adding 1, right? X squared plus 1, so I'll just put it in parentheses. You don't really need absolute values in that one. Plus c. So that's our entire antiderivative there. And the first step is a long division, and they have recently added this back into the AP exam. You might randomly see one of these, but yeah, if you see the same degree like this and you're dividing by a lot of times a binomial in the bottom, but it's same degree, x squared, do a long division, rewrite the form, and then the second piece of it is usually going to be in the form where you're going to use an ln to do the integral of that. Alright, so that's where we'll stop in this video for today.